Bill, you wouldn't have invited me to introduce Carolyn if I was just going to read out the standard biography. So obviously you want me to say something personal, which I'm delighted to do. Oh, by the way, before I do that, the tridiscophobic impulse of hotels is normally to have no 13th floor. Has anybody noticed that in the tower here, there is no 14th floor, but there is a 13th floor? I first met Carolyn Porco in 1998 in Hollywood. We were both invited to a meeting of scientists and filmmakers to try to persuade Hollywood to take science seriously and to make scientists into sympathetic characters. There was one contrarian there who unfortunately was not, was extremely influential, and he seemed to be hell-bent on destroying the whole enterprise. Jim Watson, the famous geneticist, was there. He lost patience, and he hissed a wonderfully Watsonian put-down. "Are you for real? You sound like an escapee from the Yale English department." But I was more impressed by the astronomer, the astrophysicist, the planetary scientist sitting next to this dreadful man on the same panel. It was Carolyn Porco. At one point, she quietly whispered something into his ear, and he bellowed to the entire audience, "Oh, so now she's calling me an asshole." After our panel discussion, we went on a bus tour of Hollywood, and I made a pretty shameless point of maneuvering to sit next to Carolyn on the bus. In this legendary town of starry people, I was starstruck by a charismatic scientist, which I suppose was the point of the whole Hollywood conference in a way. Carolyn then came to visit us in Oxford, and she's been a friend of Lala and me ever since. She is a planetary scientist in charge of NASA's Cassini imaging team, which is the team that brought us those stunning pictures from Saturn and its satellites, and no doubt she'll tell us about that. But she's more than just a good scientist. She's a poet. She's inspired by the poetry of science, the romance of the spheres that share our sun. She's the nearest approach I know to a female Carl Sagan, a poet of the planets, a singer of the stars. Whether or not the heroine of the book Contact was actually modeled on her, it is a fact that Carl Sagan invited her to be the character consultant on the film version of Contact. And by the way, she's also been a consultant on Star Trek. The film version of Contact gives me goosebumps, the moment when the heroine, Ellie, who I suspect is modeled on Carolyn, is woken up by the unmistakable sound of the first communication from an alien intelligence. And when she rushes back to base, screaming into the microphone, numbers, 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 the exact coordinates of where this mysterious message has come from, the spine-tingling poetry of those numbers epitomizing science. How poetically right it seems to me that the hero of those numbers should have been a woman, a role model, just like Carolyn. Just a little anecdote to display the poetry of Carolyn. A beloved professor from her days at Caltech was the geologist Eugene Shoemaker, co-discoverer of the famous Shoemaker-Levy comet. He was a pioneer of astrogeology, and he was part of the Apollo space program. He was in the running to be the first geologist to set foot on the moon. But he had to drop out for health reasons, and so he turned to training astronauts instead of actually being one. In 1997, Shoemaker was unfortunately killed in a car crash in Australia. Carolyn, in her grief, raced into action. She knew that NASA was about to launch an unmanned craft which was programmed to eventually crash land on the moon after its mission was accomplished. She managed to persuade the powers that be at NASA to add her former teacher's ashes to the spacecraft's payload. Gene Shoemaker's ambition to be an astronaut was denied him in life, but his ashes now lie on the moon's surface where no wind stirs them. It's said that Neil Armstrong's footprints are almost certainly still there. And she sent a photographic engraving bearing these words that Carolyn chose from Shakespeare. "And when he shall die, take him and cut him out in little stars, and he will make the face of heaven so fine that all the world will be in love with night and pay no worship to the garish sun." Ladies and gentlemen, the wonderful Carolyn Porco.
Thank you. I'm going to begin like I did last year, telling you a remarkable story about the inhabitants of a rocky, ocean-covered little world in orbit around an ordinary star in an ordinary galaxy. And as this story goes, these beings, just laughing at the idea of boundaries and with soaring imaginations, over time developed the languages of mathematics and science. They became masters over gravity, and eventually they flung themselves and their machines off their home planet and into, as they called it, outer space. And these beings did this merely in response to an innate desire to explore and for the joy of learning about their cosmic neighborhood and to answer questions that had vexed them and every generation of their ancestors before them. How is it that their small planet and they living on it came to be? And what was the great cosmic backdrop against which life on their planet had unfolded? Well, if you heard my talk last year, you already know the answer. This is a story about us. And we humans have been interplanetary travelers now for well over 50 years. We've been to just about everywhere you can go in the solar system. We have sent our robotic spacecraft to all the planets, all 8 of them. We have rendezvoused with comets and even landed on comets. We've landed on asteroids. We have a robotic spacecraft now only 1 month away from an official historic entry into the Kuiper Belt when it flies by Pluto in mid-July, and at that point we'll have concluded the reconnaissance of the classical solar system. And in what I regard as humanity's finest hour, we even set foot on our own moon. And we very much have been rewarded because of all these accomplishments with great insights into the origin of the Earth and its sibling planets, and we have seen with shocking clarity just exactly what our cosmic place really is. And it's a wonderful story if you sit down and you think about it. It's a story about extreme exploration, about the thrill and the intrigue of scientific discovery, and about the search for meaning. And a major chapter in the story was begun 25 years ago when an expedition to return to the planet Saturn called Cassini was finally begun. And it was a joint adventure. It has been a joint adventure between the United States and Europe. And from its conception, it called for a comprehensive, in-depth examination of everything in the Saturn planetary system: the atmosphere of Saturn, its magnetosphere, its enormous ring system, and its collection of many, many moons. And we are now in our 11th year of exploring Saturn and everything around it, and I'm going to be taking you this afternoon on a visual tour of just some of the highlights. 11 years of exploring the second largest planetary system in our solar system leaves you a lot to talk about. I can't do it all in 1 hour, so I've just cherry-picked the ones that I happen to think are, right now, I happen to think are the greatest, and that's what I'll show you. And then I'm going to conclude with what I think is the greatest legacy that this profoundly successful mission will leave behind once it's over. Now, Saturn is very far away, and Cassini at launch was very heavy. It was 6 metric tons. This is a spacecraft that is the size of a school bus, and it was outfitted to explore the second largest planetary system, and nothing was spared. And even launching it on the largest launch vehicle that we had available at the time, a Titan IV repurposed missile with solid rocket motors strapped onto that, and a Centaur upper stage on top of that, and then putting Cassini on top of the whole stack still didn't give us enough oomph to get the spacecraft directly to Saturn. So it was looped around the inner solar system twice so that it could encounter the planet Venus twice and then Earth once. This was all to pick up speed. And then, in a terribly poetic coincidence, on the eve of the year 2001, it encountered the planet Jupiter for a final push to Saturn, where it arrived 3 years later. Now, bear in mind, the object of this exercise is to get the spacecraft to its target as quickly as possible so that those of us who were involved in the mission are still alive by the time the spacecraft gets there. But all of that meant that by the time it gets there, it is going terrifically fast, and we actually have to slow it down. We have to slow down its acceleration in order to allow it to get captured into orbit. And that moment, called Saturn orbit insertion, is depicted here in an artist's rendering. We basically throw the engines in reverse, so to speak. Actually, we just take the spacecraft, turn it around, light the engines, and most of the fuel that Cassini carried at launch, and in fact 6 metric tons, roughly half of that was fuel that was expended in this maneuver to allow Cassini to get captured into orbit. And once in orbit, Cassini's tour of the Saturn system began. This was July 1st, 2004. Hard to believe it was that long ago. And then the orbital tour began, and this is cartoon of it. It's characterized by changing orbits to allow viewing of everything. We want to be in the equator plane or in the ring plane so we can encounter the moons that orbit in the equator plane. We want to jack up the inclination so that we can look down on the rings and on the polar regions of the planet and the moons, and so on. And this has been at the heart of our success, to be there for so long, be able to change your orbit, the spacecraft's orbit, to go and investigate something that you might have discovered earlier on. And so that has just worked to singular, it's worked extremely well. One of the main objectives of the Cassini mission is to study the planet itself, in particular its meteorology. And over the past 10 years, or 11 years, we've learned a tremendous amount about the atmosphere and meteorology of Saturn. We've been able to measure its wind speeds at various latitudes. We've come to understand the role of atmospheric eddies in driving the jets that are present in the atmosphere. We've investigated or been able to observe the life cycle of small-scale storms, etc. But probably the coolest thing is that it just so happened that in 2010, 2011, when we were there, we witnessed a huge, major meteorological event in the life of this planet, and that was the eruption and subsequent development of a huge lightning-producing, thundering, hissing storm in Saturn's northern hemisphere. This is the kind of storm that on Saturn comes around every 20 or 30 years. And we were there to witness it. It's certainly the largest ever observed from a spacecraft. It remained active, thundering and convecting and so on, with lightning strikes 10 times greater than any other storm we'd observed for about 2/3 of a year. And I can tell you, my team members and the people on the Cassini project who are interested in studying the atmospheres of planets are going to spend a long time studying the development of this storm. It's the kind of thing that gives you insight into how an atmosphere on another planet behaves and what makes it similar and different from the atmosphere on Earth. We arrived at the height of southern summer. August 2009, we had equinox, sun passing from the south to the north, and then we had northern spring after that. And as spring marched on in the northern hemisphere, we saw in great detail a feature that had been observed or had been discovered at the pole of Saturn by Voyager, by the Voyager spacecraft 2+ decades earlier. This is a feature everyone called the Hexagon. It is wider across than 2 Earths, and it has a jet stream which looks like it's 6-sided. It blows at something like 220 miles per hour. So many people just get into this thing that when we release anything on our website about the Hexagon, the hits go through the roof. And I think they associate it with crystal energy or something like that. They really think it's strange. We get so many questions about it. And with apologies to the New Age folks, I have to say this is nothing more than a jet stream. It's a six-sided, or a jet stream that has 6 very stable waves in it. And in that sense, it's not much different than our jet stream. This is a video taken off the website of Goddard's Space Flight Center in Maryland, and this is real atmospheric data for the Earth, and this is our jet stream, and it's very variable, it's discontinuous, but overall it has about 5, 6, 7 waves in it. You can see why we get weather patterns down from Canada along the East Coast and so on. It really determines in the mid-latitudes the weather, and the reason why Saturn's is stable and ours is not is the reason why all atmospheric systems in the giant planets last so much longer. On Earth, atmospheric systems blow over hill and dale and ocean and trees and so on and mountains, and all this wears down the momentum and breaks the system up, and then it has to start up all over again. But other than that, they're basically the same thing. So anyway, that's just an explanation of the hexagon. If anybody wants to speak to you about it being so mysterious, just tell them the truth. Surely one of the most beautiful pictures that we have taken and we in my shop have processed, and it made it all the way to Brian Williams on the NBC News in the States, is this one. It's a picture of the vortex. At the center of that hexagon, it sits right on the North Pole. It's about the size of it is half the size of the US. It's a hurricane. It blows, it has an eye wall. The speeds around it go at something like 330 miles an hour. So that's some 50% more or faster than the winds, the tornado that leveled Moore, Oklahoma a few years back. And again, this is the kind of thing that atmospheric scientists will be studying for a long time. To have the opportunity to observe another planet's atmosphere, as I've said already, gives us really an important opportunity to understand what makes our atmosphere do what it does. On Earth, one of the loveliest sights that we can see are the shifting, flickering lights of the aurorae. You guys in Canada know this probably better than anybody. Well, Saturn has them too. And here is a movie that we made of the Saturnian aurora. The stars are streaming by because the spacecraft is moving, and we are targeting the atmosphere. So we and Saturn are moving, but you can see the aurora just go whipping by with the rotation of the planet. So again, a great commonality between the two systems. It's why we went back to Saturn. The rings, of course, are what makes Saturn the icon among planets that it is. They're 280,000 kilometers, across. That's about 1 light second. They would fit nicely in between the Earth and the Moon. And they consist of countless icy bodies, colliding bodies that range in size from the finest talcum powder all the way to the sizes of small apartment buildings. And they speed around Saturn at enormous speeds of something like 20 to 40,000 miles per hour, but they very gently jostle one another. Okay, a not too bad way to think about this is traffic on a freeway. Everybody's going very, very fast, but the relative speeds are much slower. They are what is called an equilibrated system in physics. That is, any violent collisions in this system died out a long time ago. And because of that, the rings are very thin. They're only about 1 to 2 stories in a modern day building, and yet they could fit in between the Earth and the Moon. So they trace out, they're very mathematically precise. They trace out the plane of gravitational equilibrium around the planet. Bear in mind that despite their physical enormity, if you took all the mass in Saturn's rings and recomposed it into a moon of the proper density for the Saturn system, it would be no bigger than that little moon you see sitting right near the rings. I can't point to it too well, but in fact, I can't point to it at all. I hope you see it. That's the moon Enceladus. And the dark lanes in the northern hemisphere are actually the shadows cast by the rings on the planet. The rings have an enormous variety of structures, discovered in fact by the Voyager spacecraft in the early 1980s. This happens to be a natural color view of them as we made our first approach to Saturn. The smallest features in this picture are about 15 kilometers at 10 miles, so it gives you a sense of scale. Each major ring element, and that's the A, the B, and the C rings, they look very different. This could be because they have different origins. Maybe they just have different amounts of material, which we know they do, and that leads to different processes. But we're starting to get a feel for what causes all the structures in the rings. In the B ring, which is the most massive, it seems a lot of that structure is naturally self-induced. It's just waves that once the particles start moving around, the waves can slosh back and forth and they create ring features. In the A ring, a lot of the striations that we see are the linear features are actually the result of interactions between orbiting moons and ring particles. They're called resonances, and they can actually create wave features in the rings. And they also can lead to sharp edges. The outer edge of the B ring is actually the location of the strongest satellite resonance in Saturn's rings. It's a resonance with Mimas. That resonance prevents the material from spreading out beyond the outer edge of the B ring into the A ring. So satellite resonances play a big role, but also some of the most dramatic features we've seen in the rings were those caused by moons embedded inside the rings. And here's a picture of the Keeler gap. Let me go back. The Keeler gap is right at the outer edge of the A ring. It's not too good that I can't point to it, but it's not the gap that's obvious at the outer edge. It's one even closer to the edge. And here is a moon that we discovered with Cassini in that gap. Moons can actually create gaps in the rings if they're big enough, and this one is actually creating undulations in the edges of the gap because of its interactions with the particles as they stream by. It excites their orbits, it gives them a little bit of a kick and an eccentricity, and it creates these wave features. Observations like these tell us a lot about the way that moons and rings interact, and this particular moon we found is on an inclined orbit. We didn't expect that. At its highest and lowest parts of its orbit, it extends some 8 kilometers above the ring system, so roughly its width. And that was surprising. But the picture got even richer when we had the wonderful opportunity to witness a rather moving celestial event, and that was the exact moment when the sun, traveling from south to north, was shining directly over Saturn's equator and edge on to the rings. This was northern vernal equinox. This was spring arriving in the northern hemisphere, but it was lights out on the rings. Okay, the sun is shining exactly edge on. This is a mosaic that I had planned just to capture the moment. This was something no one had ever seen before, and certainly not this close. And this is a mosaic we took, and we had to brighten the rings enormously by something like a factor of 60 in order for you to see them. And this turned out to be a wonderful scientific opportunity as well. We knew it would be because the sun's rays would be shining very shallowly, and anything that protruded above and below the rings would cast shadows. And we knew we'd be able to, learn a lot by seeing the rings, as it were, pop into the third dimension. So it turned out to be great. For starters, we were amazed to see this. This is the Keeler gap again. That is Daphnis, and you could see shadows. Those edge waves are actually mountainous piles of rubble that Daphnis draws out of the ring plane as the rings go passing by and creates these waves, but they're actually mountains of rubble, extending 2.5 miles high. Just mind-blowing. And again, here's another thing that we saw. This is, difficult here without being able to point, but on the right is the outer edge of the ring system, and you can't even see the Keeler gap here because you see lots and lots of linear things that look like they're bumps. They're actually the results of the interactions I told you about between orbiting moons and ring particles. Those are at resonance locations. But if you see a really bright feature, that's a big, what we call a bending wave. That's where the whole ring plane is like corrugated cardboard. That's also caused by a resonance with an orbiting moon. But if you see that little dash, and here we're looking at it closer, this is the presence of a moonlet. At the center of this dash is a moonlet about 400 meters across, and it is responsible for agitating the ring particles around it and creating a disturbance, if you will. They take the form of these propellers. So we've kind of affectionately named all these moonlets after aviators. We have like Earhart and others. And we have seen dozens of these things, and from that we've inferred the presence of millions of them in the A-ring. And we've even had the opportunity to watch them as they drift back and forth across the rings as they orbit with the rest of the ring particles. And this is one process that we believe occurred long ago in the disk of material that ultimately became our solar system and is presently going on today in the disks surrounding young stars in which you have planets forming. You get this, what's called planetary migration. This has been discussed and in the literature for many years, and then we get to see it at work in Saturn's rings. So that is, in fact, one of the reasons we went back to Saturn, to have the opportunity to look at processes that span great spans of time and also spatial scale. And remember, I pointed out the outer edge of the B ring, which is anchored by the Mimas resonance. Well, look what we found during the equinox period. There, you could see in the lower third of the frame, maybe midway in the frame, you could see these structures that are casting shadows, lots of spiky things that are casting shadows. And this goes on for quite a long ways around the B ring. We had no idea. In all the pictures we took of Voyager, all the pictures we'd seen up until this moment with Cassini, we had no idea there was a vertical dimension to this. It was astounding. And the best that we can do, this was stuff that I did with my research group, the best that we can say right now is we think that this region is populated by moonlets that drifted across the B ring and got stuck in the resonance, and as the ring material is streaming by these biggish particles, remember, the biggest ring particles are only about 30 meters or 10 meters across. They just can't, they get squeezed together and they have no place to go but up. So anyway, it was an astonishing result, and I loved imagining that I'm flying across in a shuttlecraft. I'm flying across the rings, and the rings are only 30 feet thick, and you're low to them. So, you know, if you were doing this, it would look like the rings extended to infinity. And then you come across these structures, and they're 2 miles high. This is 2.5 miles high also. I think that ought to go in a movie. Well, one of my artist friends heard me say this at a talk, and he actually painted it on canvas. So this is the work of Michael Carroll. There's a shuttlecraft going across the rings and seeing these mountainous things, these crazy things we never expected. Okay, speaking of moons, Saturn is accompanied by a very large and diverse collection of them, and there's over 60 in all. I've shown you some of the smallest, but they range in size from a few kilometers all the way to the size of the US. And our goals in studying the Saturnian satellite system, which, you know, the inner portion is like the solar system. They're all orbiting in a plane in the same direction. We believe that you're trying to tell me something. Oh, okay, thank you. We believe that they formed out of the same nebula of material. So our goals in studying the Saturnian satellites were not only to do a survey to see if there were any more that we hadn't discovered from the Earth, not only to come away with accurate measures of their sizes, their shapes, their internal densities, their compositions, and so on, not only to advance our understanding of the geological processes that had occurred on their surfaces, but also to study the whole system with an eye towards testing and refining our ideas about the formation of solar systems, both our own and others that we are discovering throughout our galaxy today. And that's exactly what we've been doing for the last 10 years, 11 years, made possible by the orbital tour that you have seen, which is actually unprecedented in magnitude. We have done well over 100 very close satellite flybys, in some cases coming as close to a moon as 15 miles above its surface. That's only a few miles more than the altitude that you fly at if you're taking a jet from Vancouver to New York. So we're like, you know, bombarding these moons and, you know, gathering information as we go. I can't tell you everything that we've learned, but we've taken also some beautiful pictures in the process, and I wanted to show you some of them. This is Saturn with the moon Dione. It's about a third the size of our moon. And here you can see Dione closer, showing the ramparts of a crater. The moons in the Saturnian system are ice. The outer portions of them are all water ice. And here the ramparts of this crater look very fresh. Here is Hyperion. This is a very strange moon. It's a quarter the size of Dione, so it's smaller. It's got a very odd shape. It's chaotically rotating. So it's got a peculiar dynamics to it. And we understand the process by which it's come to look like this. I don't have time to tell you about it, though. Here is just a beautiful picture capturing the rings in the lower portion. You're looking up through the rings, seeing the northern shadow-draped northern blue hemisphere. And you could see the moon Mimas in the upper right. And then here is a closer look at Mimas, our Death Star. And we know that the projectile which made Herschel crater came very, very close to busting Mimas to shreds. And so it doesn't take a rocket scientist to conclude that, well, perhaps there were moons that did get broken up because of collisions with projectiles and so on. That's actually one of the ideas for how ring systems form, just the collisional breakup of a pre-existing moon. But two of Saturn's moons are truly standouts. And one of them is Titan, which is seen here alongside Saturn. Lots of beautiful images of Titan. Here's another one that looks like something painted by the Russian artist Kandinsky. I love this one. I like the black and white images, I think, the best, actually. And then here's another one of Titan with, I think that's Rhea and the rings and a small moon. Titan is 50% larger than our own moon, and until Cassini had gotten there, was the greatest single unexplored expanse that we had remaining in our solar system. And then, of course, there's Enceladus, which is seen here next to Titan. That's a small icy body, which is a tenth the size of Titan. We learned from Voyager that Titan's atmosphere was very similar to the Earth's in several ways, but it has no free oxygen, and it is suffused with small amounts of organic compounds, methane, ethane, propane, etc. And it is these compounds that make for this ubiquitous 200-kilometer deep haze that gives Titan its orange color and makes it very, very dark at the surface. At high noon on Titan, it is as dark as deep Earth twilight is on the Earth. And over time, it was suspected that these compounds in the atmosphere drift downwards, and they grow, they get larger as they fall, and they coat the surface in a blanket of organic sludge. And some of these compounds in the atmosphere, methane in particular, were expected to be liquid at the surface, despite the fact that the temperature is some minus 300 degrees Fahrenheit, which is minus 185 Celsius. That's pretty cold. In fact, water does on the Earth what methane does on Titan. Or I should have said that the other way. Methane is to Titan what water is to the Earth. And this opened up a world of possibilities. You could have patchy methane clouds floating above the surface. You could have gentle rains of liquid hydrocarbons falling down to the surface and cutting gullies and forming rivers and cataracts and carving canyons and washing the sludge off the high mountain peaks and into low-lying basins and craters and depressions. And we, because of this view that we had come to develop after the Voyager mission was over, we expected strongly, along with theoretical calculations, we expected that there should be bodies of liquid hydrocarbons on the surface, paint thinner, if you will. And so for all these reasons, just the idea that there was this incredibly exotic body that might have native organic compounds on the surface, Cassini was deliberately equipped to the gills with instruments ready to study Titan, and several instruments on the orbiter had the ability to see through the haze down to the surface. One of them is a radar instrument, which is nearly identical to the radar instrument that mapped the surface of Venus, a body with a very thick atmosphere, in the early 1990s. And this is an instrument that works with microwave radiation. It it actually pulses microwaves to its target, waits for them to be reflected, collects them with an antenna, and then those signals get reconstructed back on the ground to produce a two-dimensional image. So we were, ready to study Titan from the orbiter, and then of course there was the Huygens Probe, the deployment of which occurred about 6 months after getting into orbit, and this was a flying saucer-shaped device. It was built and operated by the Europeans, and it was carried by Cassini to Saturn, and it drifted down for 2.5 hours on a piece of fabric through the hazy atmosphere of Titan and came to permanent rest on its surface. The probe took many measurements of the atmosphere on the way down: atmospheric density, composition, winds, transparencies. It also carried cameras, and it spun as it fell. So these cameras were constantly sweeping around, taking pictures as the probe falls down to the surface. And I was there. I was one of the people there at the European Space Operations Center in Darmstadt, Germany, when this happened and was being monitored. And it was thrilling beyond measure to see the first images that were released to the public by the Huygens imaging team. And this was one of them. It was taken from 8 kilometers altitude, and it showed unambiguously a dendritic drainage pattern that could only have been carved by flowing liquid. It was like, oh my God, just, you're in one universe one moment, and you see this, and suddenly everything has changed. It was really, really thrilling. It looked, in a picture like this looks like you're looking at the coast of Naples or something. You have it turns out that the region that is carved up with the channels is about 100 meters high, so the liquid drains off into what looks like as I said, across a shoreline. At this point, we didn't know whether there was liquid or solid beyond, but eventually the probe came to rest on the surface and took this picture. That is the horizon. In the background is lots of foreshortening here. The cobbles in the front at the lower portion are almost certainly water ice, and they're about as big as a foot. They're only about this big. So this was landfall in the outer solar system. It was historic, and it turns out that the probe landed in the Titan equivalent of a mudflat, an unconsolidated ground that was wet with liquid methane, and very likely made from the accumulation over who knows how long, hundreds of millions of years, we don't know, of organic residue that had fallen out of the sky and was washed off highlands into the low-lying regions where the probe had landed by perhaps seasonal rains. And I just have to say that this part of the mission was like a Jules Verne adventure come true. It was the day humanity landed a device of its own making in the outer solar system. It was a very moving event. And as I said, I was there to watch the celebratory speeches, and there were speeches given in English, but with English accents, American accents, and German and Italian and French and Dutch accents. And as I sat there, just absorbing it all, it really just struck me very hard how this was really what the words United Nations were supposed to mean. A group of nations joined in a common enterprise, and in this case, it was to come to know and understand a planetary system that was 10 times farther away from the sun than the Earth is, and for all of human history had been untouchable and untouched, and we had just touched it with something of our own making. It was a lovely, lovely thing. But we saw no lakes of liquid hydrocarbons. It was like, whoa, where are they? That was a shocker. And then things got even more puzzling when the radar instrument on Cassini eventually discovered that there were vast dunes that girded the entire equatorial region of the moon. The equatorial and low mid-latitudes of Titan are covered, in the low-lying regions, are covered with these long linear dunes. They're about 100 meters high, about 3 kilometers apart, and these are the kind of structures that can only be created by dry particles that are lofted, can be lofted by steadied winds. It's like the Great Saharan Desert of Titan, and as I said, goes all the way around the moon, and it just was very puzzling that there was no liquid until we finally had the opportunity later in the mission to look at the poles, especially the North Pole, which was just starting to come out of darkness in 2007. And then we saw features like this. This is a radar instrument. It's falsely colored to make it more appealing, but it's a radar instrument. It shows a lake in the northern region of Titan that looks very much like the coastline of Maine. You could see in the lower left there are drainage channels that direct flowing liquid into this lake. And it has been confirmed that it's liquid hydrocarbons with other instruments on Cassini. And then eventually we found more. This is again a false color view. It's a radar sweep across the northern part of Titan. And eventually we built up a good map of the surface of Titan with radar. This is looking down at the North Pole. I think it goes down to about 60 degrees latitude. So that would be roughly like from the North Pole down to, I think, about Scotland. And you could see there's lots of liquid hydrocarbons, lots of big seas and lakes, but also smaller regions. For scale, if you scaled that up, if you scaled Titan up to the size of the Earth, that would be the size of the Mediterranean. So it shows you how much there is of this material, and we're not sure why. Oh, and then we get this very romantic picture, which is a glint of sunlight off one of those lakes in the northern hemisphere of Titan, seen by one of the instruments on Cassini that can see through the haze down to the surface in the infrared. So not radar, but in the infrared. Now, why the fluids have gone to the North Pole, we're still grappling with that. Very likely it's got to do with temperature, okay, where it's coldest. It might also have to do with geology and where the ground is more porous. I mean, there's all sorts of things we have yet to work out. So it's not at this point clear, but one thing now is very clear, and that is that after decades of speculation about what this previously unexplored moon was hiding under the haze, we now have found out, and we have found it to be an utterly remarkable place. It is the only place in our solar system where we have ponded on the surface abundant native organic compounds, also lacing its atmosphere, and a place that is exotic and alien, but at the same time very familiar, and a place that in all the solar system, in its complexity and geographical diversity, is rivaled only by the Earth itself. So Titan is one of the two bodies that we are paying particular attention to during the remaining 2 years of the Cassini mission. And the other one, as I said, is Enceladus, because despite all that we have found with Cassini, even on Titan, I think the most profound discovery we have made is what we have found capping the south polar region of the small moon Enceladus. Here is just to show you how small it is. It's about the size of England. And here is one picture that we took very early on, one of our first flybys, and it showed us that the whole moon is carved up by many generations of cracks and troughs and ridges, very few craters. So the whole cratering history of Enceladus has been completely wiped out by tectonic activity. So it has a geologic history very much unlike the other moons in the Saturnian system. But far and away, the motherlode of discoveries we have made at Enceladus was found at the South Pole. And here you're looking at what we call the South Polar terrain. The exact South Pole is about there, and you could see that it's about there, and you could see the whole region is circumscribed by a chain of mountains, just folds and ridges. They lie at about 55 degrees south latitude, so that's about Tierra del Fuego on the Earth, and everything southward of that is this very unique region on Enceladus that is characterized by 4 prominent stripes. This picture is very false colored. A natural color to your eye, Enceladus is white. It is the whitest object in our solar system. It's also the brightest. You'll learn about that in just a second. So this is very false color, and we see that these fractures that cross the surface are unique in that they seem to have different composition and crystalline size than the rest of it. Remember, as I said, the bodies in the Saturnian satellite system are mostly ice. You are looking at water ice, just lots of water ice. So we have a system of fractures. The instrument on Cassini that could measure thermal radiation, basically measure temperature, found that there was a prodigious amount of heat coming from these fractures. And then when we put Cassini in a position to look over the pole in the direction of the sun, this is what we, this is just another view of it looking more face on, taken at equinox, so you could see, goes right through the pole. But here is a picture a view you get when you look in the direction of the sun. This is a geometry that highlights, through the process of diffraction, highlights the presence of very, very tiny particles. And we saw just dozens of jets that extended hundreds of kilometers above the surface. And then when you take a picture like this and you color code the gray light levels to make it easier to discern changes, this is what you see. And you see these jets, they form a giant plume, which eventually some fraction of it, some 9% of it we know now, escapes the moon and makes it into Saturn orbit and creates one of the big diffuse rings of Saturn called the E-ring. Cassini has flown through this plume actually many times by now, and has found the instruments that can scoop up material and measure what they collect, has found that the icy particles that you see forming pictures like this, and also pictures like this, okay, that they are salty. They have a salinity that is comparable to the Earth's oceans. And they are accompanied by water vapor with trace amounts of organic molecules, even a small amount of ammonia and CO2. And these are all compounds that you will hear those of us who are interested in the origin of life and searching for life. These are molecules that we go in search of. Just light hydrocarbons and molecules that might have biologically available nitrogen, ammonia is one of them, and carbon dioxide, and so on. So the plot was getting thicker and thicker with every Enceladus flyby. And we've been able to take, in my group, this is now my research group, we've been able to take our pictures of the jets. We've taken lots of them. Like I said, this is just a sampling. The one on the top is the highest resolution we ever took. And we can triangulate, just like the surveyors of old, you know, the geologists from a long time ago would survey to determine the location and the height of a mountain, or surveyors would do a survey to figure out how to place a building. We did this. We triangulated the jets to determine where they were located, and this is what we found. We found all the jets are coming from the fractures. Some of them are very tilted. Most of them are basically vertical to the surface. And another thing we found, which was very important, we found wherever there was a jet, it seemed there was excess heat. Okay, so there was heat coming from the fractures, but we know that where it's hottest, there are jets. And all this information and other data collected from the Cassini instruments over the last 11 years now strongly indicates that these jets are geysers, and they erupt through the fractures that go 35 kilometers into the ice shell to an ocean below that is salty and is laced with organic compounds. So we are confident now that Enceladus presents to us an environment where prebiotic chemistry and perhaps even biology, even life, might be present. And in that case, it is not completely crazy that it is snowing microbes at the south pole of Enceladus. Now, Cassini is unfortunately not really equipped to answer the question as to whether or not life has ever gotten started on this moon. And in fact, a small group of us have gotten together, and we are planning a return to Enceladus properly, with a spacecraft that's properly equipped to get as close to answering that question as we are capable of doing, you know, at this point in our explorations of the planets. But I don't think that I could state it strongly enough that if we ever do discover that life has originated twice, that there was an independent genesis somewhere else in our solar system, then I think you would agree. At that point, the spell is broken, the existence theorem has been proven, and we could infer from that that life was commonplace, that it wasn't a bug, but it was a feature of the universe in which we live, and it had occurred a staggering number of times throughout the cosmos during its 13.7 billion year history. And I think that would be the final answer to probably what might be the longest standing question in human history, the kind of discovery that could change a great many things and might just get a few people upset. So, and because of all the thrills and the excitement that Enceladus has afforded us during this time, I'm holding on to one very fanciful notion that someday in the far, far future, our descendants might voyage back to the Saturn system to visit the Enceladus Interplanetary Geyser Park in a spaceship that is not unlike the Starship Enterprise. So Cassini continues. It will continue to orbit Saturn for another 2.25 years, and then we bid it goodbye. And it continues to return one beautiful image after another and deep insights into how our cosmic neighborhood has come to be. And when it is all done, I am certain that it will go down as one of the most scientifically productive missions we have ever flown. But more than that, Cassini, like all our other interplanetary explorations over the last 50 plus years, has been a story about longing, a longing to know ourselves, to understand us. And despite all the glorious scenes that we have been treated to over these many years, there is an image that says this so much better than words ever could. And it has a bit of a backstory, and I'd like to share that with you now. Back in the 1980s, I had the pleasure and the immense good fortune of hitching a ride on the greatest exploration ever, and that was the Voyager mission to the outer solar system in the 1980s. And during my 6 years on that mission, I had the pleasure of coming to know Carl Sagan and of working with him and others in planning and executing the now famous pale blue dot picture of Earth taken in 1990 by Voyager 1 from beyond the orbit of Neptune. And it's not widely known, but in a proposal that Carl had written to the Voyager project urging them to get this done because they didn't at first want to do it, he described the idea of taking this picture as the purpose of it was to take a picture of the Earth, and I quote, awash in a sea of stars. Well, the actual pale blue dot picture, if you remember it, didn't exactly turn out like that. There were no stars, and unfortunately, it showed the dot of Earth sitting on top of a beam of light that had been scattered in the optics of the camera. Of course, none of this really mattered, because it was what Carl had to say about this image, and the way that he romanced it, and turned it into an allegory on the human condition that has ever since made the phrase pale blue dot synonymous with an inspirational call to planetary brotherhood and protection of the environment. Well, since the very beginning of my tenure as the leader of the imaging team on Cassini, I have had it in my mind to do this picture over again, only make it better. And it occurred to me somewhere along the way, while I'm thinking about how this picture should be taken, what would be the right time to slot it into the parade of scientific observations so I don't, generate the ill will of my science colleagues and so on. It occurred to me how great it would be if instead of doing what has routinely been done and taking a picture of the Earth from some spacecraft and then 2 weeks later saying, hey, people, 2 weeks ago, while you weren't looking, we took your picture. Here's a picture of Earth taken from, the Galileo spacecraft or this spacecraft or that one. I thought, wouldn't it be great if instead of doing that, we told people ahead of time, on such and such a date, at such and such a time, We are going to take your picture from 1 billion miles away, from an orbit around Saturn, and invite them at that time to go out and contemplate the isolation of our planet in the blackness of space, and appreciate the rarity that it is among the sun's planets, and contemplate the marvel of their own existence and all of life on planet Earth. And so it happened. On July 19th, 2 years ago, the Cassini cameras were turned to look at Saturn while it eclipsed the sun, to take another pale blue dot image of Earth, and we sent out the word, at the moment the picture is taken, go out, clean yourself up, brush your hair, look up, think about all of us, think about your fellow humans aboard this planet, think of the magnificent achievement that this interplanetary salute between robot and maker represents, and smile. And people responded exactly the way I had hoped. Many comments came in from people all over the world stating a feeling of unity at that moment with their fellow humans. And here's just a few. This is from Sam. Phoebe, age 10, and I got the telescope out on the patio, and under a beautiful, clear, southern British sky, we gazed up at Saturn, reveling in the fact that a spacecraft was looking back on us. She asked lots of questions about Saturn, and at the appointed time, I raised a glass of fine red wine, she a glass of fizzy pop. We said cheers to Saturn, to Cassini, to each other. Then we smiled and laughed and waved and cheered and took photos of ourselves, both beaming. It was perfect. Chris, I was in Reykjavik, Iceland. We went down to the waterfront and threw a wave in the general upward direction. This is Tess from somewhere. At the appropriate time, I left the table at a restaurant and I went to the parking lot. I turned my face to the sky and I spent a few minutes watching and listening to what life on Earth was like, right there, right at that moment. What a feeling of connection and oneness with the miracle that is life on Earth. This experience was beyond meaningful. It was transcendent. What a beautiful thing. Thank you. And this is probably my favorite. This is Jolyn. I've been entranced by this project ever since I heard about it and was determined to join in the celebration. However, I never anticipated how emotional I was going to feel. I stood on the edge of Lake Ontario in upstate New York with my son and his girlfriend. I'd forgotten to bring my cell phone with its app that shows the location of Saturn, so in the end, we just spun in circles, waving at the sky. The thought that a camera was taking pictures from so very far away was just incredible. We may not be unique, we may be transient, we may be only flying along on a dust mote, but darn it, for 15 minutes, we were there, we were aware, and we smiled. And so it was a great success, and here is the mosaic. I'm sure you've all seen it. That was taken as these people and many more around the globe were thinking about our cosmic place. It's a picture I call The Day the Earth Smiled. It shows you the main rings with the sun illuminating them from behind. The sun is behind Saturn. You could see Tethys, if you can, in the lower left. That's a moon. You could see this blue ring is the exhalations of Enceladus. This is what Enceladus creates by the geysers. And then in the lower right, over the shoulder of Saturn, you can find 1 billion miles in the distance, a pale blue dot of our planet Earth, which examined even closer with our high-resolution camera on Cassini becomes the first time we've ever seen the Earth and the Moon from the outer solar system. Wow. As evidenced by your reaction, there is something very powerful about seeing ourselves, seeing our small, fragile blue ocean, Earth, as it would be seen by others in the skies of other worlds. It is, I think, that startling, uncorrupted view of who we are, where we really are, that never fails to move us. And it moves me to think about evolution. This, for me, is a picture where the biologist Charles Darwin and the astronomer Galileo come face to face. Because it is a picture that was made possible by Galileo's first experiments with gravitation over 400 years ago, and it is a picture that shouts evolution. I look at this image, and what I see are our distant ancestors stepping down from the trees and walking upright for the first time onto the African savannas and pausing to look back at the forests from which they came. And I look at this picture and I see a species that is positively relentless in its pursuit of knowledge and courageous and fervent in its longing to grasp the meaning and the significance of its own existence. And finally, I can't help but look at this picture and see the very, very best that humanity has to offer. We are, no doubt, the troubled and warlike inhabitants of one tiny little planet, and we are reminded of this day in and day out wherever we look all over the globe. But in those times of great existential despair, and I have them, and I'm sure you have them too, it would serve all of us well to remember that we are the beings that did this. We are the thinkers and dreamers and explorers who took this picture. One world, clear across interplanetary space to another. And to be this small and reach so far is, in the end, what makes us the extraordinary citizens of planet Earth. And this proud perspective is perhaps the greatest gift of all, and the legacy that Cassini and all its interplanetary explorations over the last 50 years will leave behind. And I say, let's revel in it, we deserve it. Thank you. I lost the meeting. Thank you, thank you. Thank you very much.